Good morning. Today we're looking at our homework on ideal gases, partial pressures, and some phase changes. And this has got a lot of the same kind of math that we did on our last homework assignment with a lot of algebra, and I think it'll be fun. So let's get started. First question here is asking about a flexible helium-filled balloon, and they give us some information about that. You've got an initial temperature of 20 degrees Celsius. We have an initial volume of 5 liters and an initial pressure of 760 millimeters of mercury. Then they tell us that this balloon ascends to this altitude where the pressure is, our new pressure, 76 millimeters of mercury. The temperature is minus 50 degrees Celsius. And they want to know what is the new volume. All right, so in order to solve this, we've got multiple variables here, more than we did before, and we're going to use this, what we call a combined gas law, which puts together the individual gas laws that we had previously. So for previously we said P1 V1 equals P2 V2, and we also previously said that P1 over T1 was equal to P2 over T2, and we also said that V1 over T1 was equal to V2 over T2. And if we put all of these things together, just to see what the relationships are between them, we see that P1 V1 over T1 equals P2 V2 over T2. And in fact, if this is the only one that you memorize, then essentially if temperature is constant, you could eliminate that and you could be left with Boyle's law. Or if volume is constant, you can cancel those out and you could be left with this one here. So hopefully you can see if you memorize just the combined gas law, then you can deduce these other ones from it. That might make your life easier. But in this case, we are given T1, V1, and P1, and T2 and P2. We just need to solve for V2. And again, I'm going to recommend that we solve for V2 before we plug our stuff in. So in order to get V2 by itself, I need to multiply both sides by T2. So T2 will cancel. And then I need to divide both sides by P2 so that the P2 will cancel. And now we get V2, which is what we're looking for, is equal to P1 V1 T2 divided by T1 P2. Okay, so P1 was 760 millimeters of mercury. And I always include the units just to make sure that I don't make any mistakes. V1 is 5 liters. And T2 is negative 50 degrees Celsius. Remember, we can't use Celsius. We have to use Kelvin. And to convert, we're going to add 273.15 to each of these. That'll convert us to Kelvin. So 273.15 minus 50 is going to be 223.15 K. Now I divide by T1, which is going to be 293.15 K. And divide by P2, which is 76 millimeters of mercury. And hopefully you see kelvins cancel. Millimeters of mercury cancel. We're left with units of liters, which is great because that's what we're solving for, is volume. So if I just plug these in, 760 times 5 times 223.15 divided by 293.15 divided by 76 gives me a final volume of 38 liters. All right, let's plug that in. 38 liters. There we go. This next problem is exactly the same. Now we're going to say our initial volume, V1, 4.8 liters. Initial pressure, 365 millimeters of mercury. And our initial temperature, 20 degrees Celsius, plus 273.15 is going to make it Kelvin. So that's going to be 293.15. And finally, we see our temperatures increase to 37 degrees Celsius. So T2 equals 37. Add that to 273.15. And it looks like we're going to get 310.15. And containers compressed to 2.90 liters. So V2, 2.9 liters. And they want to know what P2 is. Okay. So set up the same way. If P1 V1 over T1 equals P2 V2 over T2, we need to get P2 by itself. So I'm going to divide by V2 and multiply by T2. So I get P2 by itself. More space here. So T2 is 310.15 K. P1, 365 millimeters of mercury. V1, 4.8 liters, divided by T1, 293.15 K, divided by V2, 2.9 liters. My kelvins cancels, my liters cancel, and I'll be left with units of millimeters mercury. So 310.15 K multiplied by 365 millimeters mercury multiplied by 4.8 liters divided by 293.15 K divided by 2.9 liters, and I get 639 millimeters of mercury, the unit that's left. Do note that your number values might be different from my number values. So don't just try to plug in 639. If you got it wrong, make sure that you're using your numbers to set up the problem. Next, here we go. We're given some information about a volume of hydrogen gas that was collected, and then we change the conditions under which that is, and we want to know what the new volume is. So using the combined gas law, we can see that originally V1 that was collected was 77.1 milliliters. Original temperature, 23 degrees Celsius, so add 273.15, that's going to be 276 to 96.15. And initial pressure was at 748. They want to know what the new volume is. If we're at 0 degrees Celsius, plus 273.15 to make that Kelvin, and 1 atmosphere of pressure. All right, solving for V2, P1 V1 over T1 equals P2 V2 over T2. To solve for V2, I'm going to multiply both sides by T2, so those will cancel. divide both sides by P2. So those will cancel, and now I'm solving for V2. So T2, 273.15 Kelvin. P1, 748 millimeters of mercury. And V1, 77.1 milliliters. Divided by P2, 1 atmosphere. And T1, which is 296.15 Kelvin. And now we see that the kelvins cancel. And look at that. These do not cancel because I don't have the same units of pressure. All right, I did that on purpose so that you could see if you include your units that it'll tell you when you've got a problem. And the problem is that these either both need to be in atmospheres or they both need to be in millimeters of mercury. Doesn't matter which, because they'll cancel, but they need to be in the same units. So again, you don't have to memorize this, but 1 atmosphere, you could look this up, is 760 millimeters of mercury. I'm just going to insert that right here for 1 atmosphere. There we go. Now our millimeters of mercury cancel, and I'll be left with units of milliliters, which is a unit of volume. That's what I'm looking for. So if I plug this in, 273.15 Kelvin multiplied by 748 millimeters of mercury multiplied by 77.1 milliliters divided by 760 milliliters of mercury divided by 296.15 Kelvin, and I get 69.98 or 70.0 milliliters of gas. Perfect. Multiple choice. This is what this type of problem is going to look like on the test. So let's try this one. Sample of helium has this volume. Okay, so V1, 480 milliliters. T1, 47 Celsius. It'll make it K. And P1, 740 millimeters of mercury. The temperature is lowered to 22 degrees Celsius. Pressure changed to 625 millimeters of mercury. And what is the volume? And they're giving us units of milliliters. That's what they want. Okay. P1, V1 over T1 equals P2, V2 over T2. We're solving for V2, so we have to multiply both sides by T2 and divide both sides by P2. And now we get V2 is equal to T2 P1 V1 divided by P2 T1. Okay. T2, 22 plus 273.15. P1, 740 millimeters mercury. That's going to be Kelvin. And V1, 480 milliliters. Divided by P2, 625 millimeters mercury, and T1, 47 plus 273.15 Kelvin. And the kelvins will cancel. Millimeters mercury cancels. We'll be left with units of milliliters, which is what they want, so we know we did it right. So here we go. I'll put this in parentheses, 22 plus 273.15. That's our new Kelvin temperature for that. Multiplied by 740, multiplied by 480, divided by 625, divided by 47 plus 273.15. gives me a new V2 of 523.94 milliliters. That is right there. Okay, so that is the combined gas law. What we're going to do next is called the ideal gas law, which instead of having us compare initial conditions to final conditions, it gives us one equation that we can use to calculate any other variable if we know all of the other conditions based on the way that all gases behave. And this is the ideal gas law. PV equals nRT. I will give that to you on a test. You do not have to memorize it. And the value of R actually changes depending on what units we're using. But in this case, we're always going to be using these units and this value. I will give this to you. You do not have to memorize it. So I'll give you the ideal gas law and I'll give you the value of R. But this is what we're looking at. The pressure times the volume of any gas will be equal to the number of moles times the gas constant, R, times the temperature. And R equals 0.0821 liter atmospheres per mole Kelvin. And one important thing to note is that in order to make this work, since R has these units, then our PV, N, and T must also reflect those units so they can cancel. So pressure, for the purposes of this equation using this value for R, pressure must always be given in atmospheres. And volume, for the purposes of this equation using this value of R, must always be given in liters. And N will be number of moles, and T always has to be Kelvin. All right? Okay, so looking at this particular first problem, we've got a balloon. The temperature is 21 degrees Celsius. Okay, so T equals 21 Celsius. Let's do 73.15. That's going to make it 294.15 Kelvin. Right? The pressure is 0.700 atmospheres. My neighbor tells me that that balloon has 4.5 moles of gas. Number of moles, 4.5. N for number. So the question is, what is the volume? Now I've got 1, 2, 3, 4, 5. It looks like 5 variables, except one of these is a constant. So we know what R is. They gave us T and P and N, and we just need to solve for V. So again, take this equation and solve for what you want before you plug it in. If we want to solve for V, we better divide both sides by P. V equals nRT over P. So V is equal to 4.5 moles, 0.0821 liter atmospheres per mole K, and T, 294.15 K, divided by P, 0.700 atmospheres. Again, note that I kept all my units and I can see moles divided by moles, K divided by K, atmospheres divided by atmospheres. I'll get an answer in units of liters, and since they asked for a volume, that's exactly what I should get, so I know I did it right. 4.5 moles multiplied by 0.0821 liter atmospheres per mole degree Kelvin, multiplied by 294.18 Kelvin, sorry, 0.15 Kelvin, divided by 0.700 atmospheres, gives me a volume of 155 liters. That's a big balloon. All right, next we've got a tank here with 20 liters. That's the volume. So volume 20 liters. It's filled with 7.20 moles of gas. So N, number of moles, 7.2 moles. Stored at 45 degrees Celsius. That's quite hot. and they want to know what is the pressure. So solving PV equals nRT for pressure. Divide both sides by volume, and we get P equals nRT over V. So P equals 7.2 moles times 0.0821 liter atmospheres per mole K, multiplied by, here we have 45 plus 273 Kelvin, divided by 20 liters. Moles cancels with moles, Kelvin cancels with Kelvin, liters cancels with liters. We're left with atmospheres, which is what we want for pressure, so we know we did it right. I can plug this in. 7.2 moles times 0.0821 liter atmospheres per mole Kelvin times 45 plus 273.15 gives us Kelvin temperature of 318.15. Divide that by 20 liters, and that gives me a pressure of 9.4 atmospheres. All right. Our first question we solved for volume. This next question we solved for pressure. Now they want us to solve for number of moles, N. We can do that. This is all just algebra. And we are professional algebra people. PV equals nRT. To get N by itself, we're going to divide both sides by R and by T. So PV over RT is equal to N. And what we see is that our volume is 160 liters. Temperature is 985 degrees Celsius. Add 273.15 to make that Kelvin. Pressure is 1.1 atmospheres. And they want to know how many moles of air. And notice this is air. This isn't even an individual gas. This is just a mixture of gases, because of course air has oxygen and it has nitrogen and it has water vapor and it has other molecules as well. But it doesn't matter because all of the gas particles behave the same way. So I could just say how many moles of gas particles, even if it's a mixture. So like air, we can still plug it all in. So number of moles equals the pressure, that is 1.1 atmospheres, multiplied by the volume, 160 liters, divided by R, 0.0821 liter atmospheres per mole K, divided by the temperature, which in this case 985 plus 273.15 K. Atmospheres divided by atmospheres, liters divided by liters, Kelvin divided by Kelvin, and now I have 1 divided by moles, which actually puts moles back on the top. So I've got the right unit, so I know I did it right. Let's plug it in. 1.1 atmospheres multiplied by 160 liters divided by 0.0821 liter atmospheres per mole degree Kelvin divided by 985 plus 273.15 Kelvin, which gives me a Kelvin temperature of 1258.15, and the number of moles is 1.70 or 1.7. All right. And finally, they want us to calculate temperature, right? We've solved for everything else using the ideal gas law. We can do that. PV equals nRT. If I solve for temperature, I'm going to divide both sides by N and divide both sides by R. We see that PV over NR is equal to T. And we're given volume equals 18 liters. Number of moles, N, is and the pressure 3.2 atmospheres. We plug this in, 3.2 atmospheres, 118 liters, 4.4 moles, and 0.821 liter atmospheres per mole Kelvin. Atmospheres cancel, liters cancel, moles cancel. 1 divided by 1 over Kelvin gives us an answer in Kelvin. Oh, and be ever so careful here that when you're transcribing the R value, which I give you, so you don't have to memorize it, it's 0.0821. That was a mistake. It's almost off by a factor of 10. So I need to divide by 0.0821, and that gives me the Kelvin temperature of this cylinder. Now they want Celsius. Of course they do. So if this is the Kelvin temperature, then I need to subtract 273.15, right? Because again, Kelvin equals Celsius plus 273.15. That's what we've been doing throughout. So now if I know my Kelvin, then my Celsius equals the Kelvin minus 273.15. So here we go. That's my Kelvin temperature minus 273.15 gives me a Celsius temperature of negative 113 or negative 114 degrees Celsius. So that is the ideal gas law. We've got a couple additional questions on it, but by this time we're professionals. We've already used it to solve for pressure, volume, temperature, and number of moles, so no problem. If we've got 2.1 moles of oxygen, that's got to be N for number of moles. Volume of 24 liters. Pressure 1.5 atmospheres. What is the temperature? PV equals nRT. Solve for temperature, divide by N and R. So PV over NR is equal to T. P was 1.5 atmospheres. V is 24 liters. N is 2.1 moles. And R is 0.0821 liter atmospheres per mole K. And I get units, liters cancel, atmospheres cancel, moles cancel. K will be on the top, and they want units of K, so I don't have to convert to Celsius when I'm done. That's nice. 1.5 times 24 divided by 2.1 divided by 0.0821 gives us 208.8. We'll round that up to 209 Kelvin. Next, we're looking at the rate at which carbon dioxide is exhaled by an average adult at rest. And here they give us milliliters per minute, but they want moles per minute. So that's nice. The minute part doesn't change. We just need to change from the milliliters to the moles. So the way that's going to look is to say, look, my initial volume for every minute is 240 milliliters. My initial temperature, 37 Celsius. Add that to 273.15. It's going to be 310.15 Kelvin. 1 atmospheres of pressure. And they want to know moles per minute. So I just want to know, since this is the amount of volume in 1 minute, then I can calculate directly for the number of moles that have been exhaled in that same amount of time, and that will give me moles per minute. So if PV equals nRT, solve for moles, I'm going to divide both sides by R and divide both sides by T, and N equals PV over RT. So that is 1 atmosphere, 240 milliliters divided by 0.0821 liter atmospheres per mole K, and 310.15 K. Now atmospheres cancel with atmospheres, and milliliters, oh, do not cancel with liters. So in order to make this work, I have to convert milliliters to liters so that they will cancel. So move that decimal point over. This is 0.240 liters. 0.240 liters. Okay, now liters will cancel. Kelvin will cancel, and 1 divided by 1 divided by moles gives me units of moles. So I'll plug these in. That gives me 0.0094 moles. Next, we're looking at some information on a hot air balloon. And if you read the question, it might feel like you don't have enough information to calculate what you need. But I assure you that you do, and we can use the ideal gas law. And let's just kind of muddle through it, see how far we can get. So to start, we see a hot air balloon has a volume 1.6 times 10 to the 5th liters, and a temperature of 370 K, and a pressure of 0.985 atmospheres. The first question says, if air has an average molar mass 29 grams per mole, then what they want to know is the density of the hot air balloon. And density is mass over volume, but you don't have to memorize that formula, because you could just look right here and see, oh, they want, whatever they want here, they want units of grams per liter. Now I already have grams per mole, so now I just need to convert from moles to liters. So if I can find out the number of moles, that I can see what the conversion is between moles and liters, and I can apply that with dimensional analysis. So we're here going to put together what we know about dimensional analysis with what we know about the ideal gas law. So PV equals nRT. We've been given P, we've been given V, R is a constant, and we've been given T. So we can solve for moles N by dividing by RT. So N equals PV over RT, so that would be 0.985 atmospheres times 1.6 times 10 to the 5th liters divided by 0.0821 liter atmospheres per mole K, and 377 K. So atmospheres divided by atmospheres cancels, liters cancel, kelvins cancel, and moles go on top. And we see that this hot air balloon has (5091) moles. All right, so we see now that 5091 moles is the size of our sample in terms of moles, and we know that that equals 1.6 times 10 to the 5th liters for the purposes of this gas. So this is a conversion factor. I could take 29 grams per mole, which is the molar mass, and convert from moles to liters just like this. There are 5091 moles in this same sample, which contains 1.6 times 10 to the 5th liters. Moles will cancel, and I will be left with units of grams per liter, which is what they wanted. So 29 times 1591 divided by 1.6 times 10 to the 5th gives me a density of 0.923 grams per liter. Okay. Now, how does this compare with the density of air at STP? You can guess that a hot air balloon is going to be less dense than air, because otherwise it's not going to float. But we don't have to guess. We can actually calculate that because we know that STP has a temperature of 0 Celsius, which is 273.15 Kelvin, and has a pressure of 1 atmosphere. And we know that for every 1 mole at STP, we have 22.4 liters. That's Avogadro's law. 1 mole occupies 22.4 liters at STP. And you could actually calculate that using the ideal gas law. Just solve for liters if you plug in 1 mole. But this is what we know about air. And we also know that we're still talking about air. And air has an average molar mass of 29 grams per mole. So we can still use that. 29 grams per mole. And 1 mole STP, 22.4 liters. So air at STP has a density of 1.29 grams per liter. That is higher than this one. So this is lower, it's less dense, and we can prove that mathematically. Right. Last question in this section. Calculate the volume of 5 moles helium. So N equals 5 moles. Temperature 120 degrees Celsius, which is 393.15 Kelvin. And pressure equals 1520 millimeters mercury. I'm going to need that in atmospheres. So 760, 1 atmosphere. That's 2 atmospheres. They want volume. Solve for volume by dividing both sides by P. We get 5 moles. 0.0821 liter atmospheres per mole Kelvin, and 393.15 Kelvin over 2 atmospheres. So moles cancel, Kelvins cancel, atmospheres cancel, left with liters, which is what we wanted. 5 times 0.0821 times 393.15 divided by 2 gives me 80.6 liters. Excellent. All right, now we're looking at mixtures of gases, and we saw a little bit of this when we did the hot air balloon problem, because air was a mixture of gases and we just treated it like it was just one big gas, which in fact it is. And that's how we can treat mixtures of gases. So here we're saying the total pressure equals the sum of the pressures of each part. So if I wanted to solve for just one, then I could take the total pressure and subtract the other two, and that's what we're doing here. Solve for the pressure of helium if I know that the total pressure is 1 atmosphere and that you get this much from the nitrogen, this much from the oxygen, then there's this much helium left, as an example. So here, for the question, they say we've got a mixture of helium, argon, and xenon. Total pressure, P tot, equals 3 atmospheres. Pressure of the helium, 0.4 atmospheres. Pressure of the argon, 0.450 atmospheres. So what is the pressure of the xenon? Well, since the total pressure equals the sum of these, I could solve for the pressure of the xenon by subtracting these out, and we see that 3 minus 0.4 minus 0.45 is going to equal pressure of the xenon. 2.15. Your numbers might be different than mine, remember. Next, we've got a volume, 18 liters. This volume contains 0.250 moles of N2, 0.250 moles of O2, and an unknown quantity of helium. We're given that the temperature is 0 degrees Celsius, that's 273.15 K, and the total pressure is 1 atmosphere, and we, of course, we're told the volume is 18 liters. So they want to know how many grams of helium gas are present. So the first thing we're going to do is say, look, PV equals nRT, because they gave me pressure and they gave me volume and they gave me T, so I can calculate the total of moles pretty easily there. And this works just as well for mixtures of gases, so this is okay. I'm going to calculate number of moles. N is going to be equal to PV over RT, because I divide both sides by RT. So N is equal to 1 atmosphere, 18 liters, 0.0821 liters atmospheres per mole K, and 273.15 K. Atmospheres cancel, liters cancelled, Kelvin cancels, and I'll be left with 0.8027 moles. Now, since I have 0.250 moles of nitrogen and 0.250 moles of oxygen, and if the rest is helium, that I have 0.303 moles of helium. And since the periodic table tells me that helium weighs, let's pull this up here, 4 grams per mole. Just set that up dimensional analysis style and calculate that there must be 1.21 grams of helium present. Now I actually made that a little bit harder than it needed to be, because I could have remembered that if they're looking at 1 atmosphere and 0 degrees Celsius, I'm looking at STP. Remember, at STP, 1 mole of anything is 22.4 liters. So I could have just said, if I have 18 liters and at STP I've got 22.4 liters in 1 mole. So 18 divided by 22.4 gives me 0.8035 moles right here. Minus 0.25 minus 0.25 leaves me with 0.303 moles of helium, and then I could plug that in, multiplied by 4.003 grams per mole, that's 1.21 grams. So either way, get the same answer. It works really well. Okay, next question on mixtures of gases. The partial pressure of oxygen in air at 1 atmosphere is 160 millimeters of mercury. They're saying here now, if the p-tote is 1 atmosphere, then the pressure of just the oxygen is 160 millimeters of mercury. And they want to know if the atmospheric pressure is 435 millimeters mercury, then what is the pressure of the oxygen? And the key here is to recognize that oxygen is going to occupy the same percentage of air, so it's going to have the same fraction of the pressure. But this was given in atmospheres, and this is given in millimeters mercury, so we need to convert that to 760 millimeters of mercury. So the fraction of oxygen compared to the total is 160 over 760. And that's going to be the same. The fraction won't change. The pressure might, but the fraction won't change. So if I'm at 435, then my total pressure has gone down, and so will the pressure of the oxygen. Or in other words, we're saying, hey, look, looks like the oxygen is 21% of the air. It's exerting 21% of that pressure. So 21% of the total 435 pressure gives me a partial pressure of oxygen of 91.6 millimeters of mercury. This is a very similar problem, except instead of going on a high mountain that has a very low pressure, now I'm going to look at a situation where I have a higher pressure of one thing. But in fact, this is an easier problem. It's telling you that the fraction is 45%. Remember, at our last problem, the fraction was 21%. So that's the fraction. And if the atmospheric pressure, 753 millimeters mercury, then what is the X? How much of that is oxygen? So at 753 millimeters mercury, 45% of that is oxygen, then 45% of the pressure comes from the oxygen. So the pressure that the oxygen is exerting is 338.85. Now note, this says 340. This is in an oxygen tent. This was our normal oxygen at atmospheric pressure. So this is twice as much oxygen. That's why this is an oxygen tent, because it delivers more oxygen to the tissues. All right, we've got an interesting conversation here about changes of state. And because we've been talking about gases and how these particles are really far apart from one another. And we previously talked about solids and liquids and how they're held together with intermolecular forces. This is going to look at some of the energy required for some of those changes. So we've got a little video here, and it talks about how basically going from a solid to a liquid to a gas, your particles have enough energy to overcome those intermolecular forces, and so on and so forth. So please watch the video if you haven't already watched the video. If you have watched the video and you're curious, then follow me here. We're going from low temperature to a high temperature. Down here we're at the solid, and eventually we made it all the way up to the gas, right? So at this point we're solid, but we're warming up, so we're heating the solid. And then the temperature stops increasing, but the energy that is going into the system is doing this phase change, solid to liquid. That's known as melting. Now here I'm at a liquid, and I'm warming up, so heating of the liquid that goes here. And then again, the temperature stops increasing, and all of that extra energy goes into breaking those intermolecular forces, and that takes you from liquid to a gas. That's known as boiling. And finally, once you're all in the gas, you warm that up, and we're heating the gas. That's what that heating curve represents. All right, so we want to know what the average kinetic energy of the molecules for the following option is in decreasing order. So highest kinetic energy, lowest kinetic energy. And you know that the more you increase the temperature, the more kinetic energy you're giving them. So after point D is a gas. Those are going to be the highest kinetic energy because we're up here. Between B and C is right here. And before point A, that's down in the solid. That's the lowest. So B and C is liquid. So here I am a solid, here I am a liquid, and here I am a gas, right? Before point A, I'm just warming the solid. I'm still solid. Between here and here, I'm warming the liquid. I'm still liquid. And above here, I'm warming the gas, but that's still a gas. So this is really just another way of saying gases have more energy than liquids, which have more energy than solids. Next, are these processes going to absorb energy or release energy? Or in other words, they're saying require the input of energy, that is absorbing energy, and this is releasing energy. So vaporizing is when we go from a liquid to a gas. Since gases have more energy than liquids, that's what we just did here, then in order to get more energy, I'm going to have to put more energy into it. So that is going to require an input of energy. Deposition is the process of going from a gas directly to a solid. A gas directly to a solid. And since solids have less energy than gases, that energy has to go somewhere, so it is released. Melting is a process of going from a solid to a liquid. Since solids have less energy than liquids, I have to absorb energy in order to make that happen. Condensing is going from a gas to a liquid. Liquids have less energy than gases, so I must be releasing energy in order to go to a lower energy state. Subliming is going directly from a solid to a gas. It's the opposite of deposition. Solids have less energy than gases, so in order to go straight to a gas, I have to absorb an enormous amount of energy. And freezing is going from a liquid to a solid. Liquids have more energy than solids, and so that energy is going to be released. Notice that the opposites, right? If deposition is the output, then subliming is the input, right? That's gas to solid, that's solid to gas. Melting is solid to liquid. Freezing is liquid to solid, so they're opposites. And same thing with vaporizing and condensing. Next, which process is exothermic? This is exactly like that little sorting thing that we did. Exothermic, I have to go from a higher energy state to a lower energy state so that that energy can be released. That's what exothermic means. I'm releasing energy. So let's look for higher energy to a lower energy. Solids are very low energy, so that's not going to work. Gases are very high energy, so this is higher energy to lower energy. Gases are very high energy, so that's got to be the right one. Next, we can actually calculate how much heat we can remove in the process. So here's the heat of vaporization. That's the amount of energy it's going to take to evaporate the alcohol. And there's nothing fancy about this. We could just use dimensional analysis to solve the problem. So we have 190 grams of alcohol. And we see that the heat required to vaporize it, that is to go from a liquid to a gas, is 159 calories per gram. So how much heat could be removed from the skin if I evaporate, that is go from the liquid to a gas, for 190 grams? Grams cancels, and I'm left with units of calories, which is what they asked for. That's a unit of heat energy. And that's 30 to 10. And finally, heat of fusion of acetic acid, which is change in heat going from the solid to the liquid. And by the way, this is both directions, right? It's just that going from liquid to the gas would absorb 159, gas to the liquid would release 159, going from the solid to the liquid will absorb 45.9, going the other direction would release 45.9. This is for acetic acid. And they want to know, all right, if I'm melting, and again, that is the solid to liquid conversion we've got here. They've got 2.45 moles of solid acetic acid. Uh-oh, they didn't give me grams. I'm gonna have to take an extra step. Moles of acetic acid. And we need to go from grams per mole. So acetic acid is this acetate with hydrogen that makes it an acid. So that's 2 carbons, 2 times 12.01, and 4 hydrogens, and 2 oxygens, for a total molar mass of 60.052 grams per mole. And now that I've got grams, 45.9 calories per 1 gram. So 60.05 times 2.45 times 45.9 gives me, oh, and now they said kcals, not cals. So I do have to take this extra step. Always look at the units they're asking for and make sure you've got those. There are 1,000 calories in 1 kcal, because the kilo means the same thing, no matter where you're at. So 6.75 kilocalories. Okay, that is it. I hope this was helpful. Have a great day.